I'm really happy, just on time. Phew. Okay, so our first guest is Mr. Manu Kapur. Mr. Manu Kapur is currently the director of the Singapore ETH Center and a professor of learning science and higher education at the ETH Zurich, Switzerland. Before this, he worked in Singapore and Hong Kong, heading learning science labs and initiatives. Manu is widely known mainly for his work on learning from productive failure. Mr. Kapur, the floor is yours.
Thank you, Antonio, and good morning, everybody. It's a shame we have to sit all in here in such dark when it's so beautiful outside. But it's lovely to be back in Parma. This is my second time here. First time was on holiday, this time is on work, but I'll make some time. So I'm a learning scientist. It's kind of going back to the basics. I look at fundamental mechanisms of how we learn, so all the way from physiological, neural, cognitive, social, and cultural mechanisms. And then I use them to design interventions and applications. And at the same time, I can look at any environment or any application or a method and evaluate it vis-a-vis the basic mechanisms of learning. And today, what I'm going to share with you is a side gig of mine, which started a few years ago because of the pandemic, when we started looking at flipped learning. It's an idea that is very popular, very familiar to all of you, I'm sure. So let's look at what the basics of flipped learning tell us, and the research around it. But I want to go back first into a time where I was a math teacher. So I taught math for 4 years for grade 12 students. And as a math teacher, my philosophy was very simple. If I can explain the concept as clearly and as logically as possible, and show them exactly what to do and how to think about it, perhaps my students would understand what I was talking about. So I did that. And students even liked my lectures, at least they said so. Right? Yet, when I tested them afterwards, I found that many of them could do what I was showing them, but you change a little bit, and they were completely lost. Right? That must be a story that's familiar to all of you as well, as I understand most of you are teachers and educators yourself. So what did I do when I found out my own students were not able to go just outside what I was trying to teach them? I would teach the same thing again, this time even more clearly, more engaging perhaps. We call it remediation. And yet the phenomena persisted. I could not for the life of me understand why was it that what I could see so clearly and explain arguably very clearly as well was not working. It was not working in the sense that they could do what I was trying to show them, but they could not adapt and move on to novel things. You just had to change a slight thing, and they faltered. And later, as I became a learning scientist and I started to do my research, my PhD, and so on and so forth, that is really our current model of education. I know we don't know what might happen next week, but education practices are very persistent because education cultures are very persistent. And direct instruction is one of those methods that is so intuitive, as it was for me as a teacher, that if you want to teach a novice something new, the best way to do it is to just tell them exactly what to do and how to do it. What could possibly be wrong with that? Except for almost 4 decades now, we've known something is wrong for that, both in my experience and on the basis of research. And this was a study from Alan Schoenfeld out of Berkeley, a very seminal paper, catchy title, When Good Teaching Leads to Bad Results. And he and his colleagues went into math classrooms, and these math classrooms were taught by very good math teachers. Right? And if you observe these classrooms and say, yeah, this is a really good lecture, this is a very good teacher. If you ask the students, just like I did mine, they too would say, yeah, I could understand everything that the lecturer was saying. Yet, when you came out and you assessed them on conceptual understanding and transfer, the understanding was really shallow. Exactly. If you change slightly, they would falter. Hence, the disasters of well-taught mathematics courses. And it's a phenomenon not just in math, it's more universal. And I use this, both my experience and this study, to articulate the problem of initial learning, the problem of learning that we're trying to counter. Because if you don't understand the problem, you won't hit the solution that works, right? So the problem is not that we learn poorly from bad lectures. I hope this is not a bad lecture, but if it is, you learn very poorly. The problem is that we learn poorly from very good ones. So I don't expect you to take a lot out of this today, even if I'm good. But you have to understand the problem. The problem is that we learn poorly from very good lectures. And there are several reasons from a cognitive standpoint that we understand now why that is the case. Okay? But that's the problem. And against this backdrop of the problem, we started to look at, is flipped learning a solution to this problem? Yeah. So let's look at flipped learning. And this culminated in a paper that I wrote with my colleague John Hattie and our two senior postdocs at the time, Irina and Tanmay. And I'm going to share some of the thinking and the work that went into this paper. This was published about 2 years ago. So if you look at flipped learning, it's first a direct instruction, like I said. It's really a method where you instruct, where you have instruction in the classroom, typically, followed by more application and problem solving. So very simply put, it's instruction first, even very good instruction, hopefully first, followed by application, problem solving, and so on and so forth. The idea of flipped learning, as we understood from the research, from our review, was, well, let's take the instructional component, which is deemed to be passive, mostly, to an online modality, so that you can save classroom time for more active learning, problem solving, and so on and so forth, okay? And so that was flipped learning. Take the passive component of classroom instruction online. So basically, it's a passive online modality followed by an active, supposedly an active in-class modality. However, if you think of the learning method, when you're coming to learn and understand something new, the pedagogy remains the same. It's instruction first, followed by problem solving or an application. There is no change per se in the method. The learner is going through the same process. They see a lecture or a video, followed by problem solving and application in class. And therefore, from a basic cognitive mechanism standpoint, we should not see any change in the effects on learning. Although, it would be very surprising that if the underlying pedagogy is the same, that we start to see any effects. That would be very surprising. And the only way to find this out was to actually do a meta-analysis of all the flipped learning interventions against traditional instruction. Right. So when we started looking at meta-analysis, we already found that there were 46 at the time, right? Ours was the 47th. There were 46 meta-analyses already. And many of them were pointing to a positive effect of flipped learning. So we were wondering what's going on, right? Second, out of all these flipped learning interventions, we culled out the ones that were really good, strong experimental studies. We found 173 studies on flipped learning, and it is on these that we started to do a meta-analysis. So here's the first finding. We found, contrary to what we thought, because the underlying pedagogy is the same, we found there was a positive effect in favor of flipped learning. And it was not a small effect, it's a 0.4. It's about a year of schooling effect. So this is a very good effect size in educational interventions. So what's going on? We did find there was a lot of heterogeneity. In other words, there's no true effect size here because there's a lot of variation around this mean effect size. That means sometimes it was working very well, sometimes it was at the midpoint, and other times it was not working very well. So we wanted to find out, why is it? What's mediating this variation around the mean effect size? And that's where we went back to, looking at coding the flipped learning interventions. It turns out that nobody, at least by that time, nobody had actually bothered to look at what was happening both online and offline or in classrooms, what kinds of activities were taking place in these flipped learning interventions, right? And so we coded them for active learning versus passive learning. And what do I mean by that? So you probably have heard of Mickey Chee's ICAP framework, interactive, constructive, active, and passive. And the idea is that as you design activities that are passive, you move them up to active, to more constructive, and then interactive, the learning effects increase steadily. That's the thesis, right? And she's shown through multiple studies that this broad pattern kind of maintains, right? And so we used the similar definitions of active versus passive. We didn't break it down into 4 categories. We just broke it down into 2, active versus passive. We went into each paper and we looked at what was happening online, what kinds of activities were designed online, right? There were readings, there were videos, there were quizzes, there were PowerPoints, and so on and so forth, which is as what you would expect in the online modality of a flipped intervention. And then we went and looked at what was happening in class. Was there problem solving? Was it clickers? Was it group work? Etc., etc. And for each paper, we coded them into these categories. So now we had a good sense that if people are saying that this is a flipped learning intervention, what exactly, at least in the broad course categories of active versus passive learning, what was happening? And what do we find? So this is where it gets really interesting. So remember, the average effect of flipped learning was positive, and it was a fairly strong effect of a year of schooling, right? So where is that effect coming from is what we dove into next. What we found that on average, there were more passive online activities, as expected, but we also found that the in-class activities were also very passive. Okay? In other words, the quality of implementation in many of the flipped learning studies was not consistent with their basic hypothesis that let's move passive online and active in class. It turns out it was more passive online, as expected, but also more passive offline. So in other words, the effect was coming from passive learning activities. If this is working, yeah, because there was low prevalence of active learning overall. And even when active learning was present, this really surprised us, that the effect was not, it did not create an effect. Right? So think about this. You have an average effect that's strong, but it's really coming from passive and more passive learning activities. And so much so that if there was active learning designed for, it was not creating an effect. Okay? The largest impact of flipped learning interventions was when there was actually a lecture in class, which totally defeats the purpose of flipped learning, right? It's like if you have to go video online and then you have to come back in class to give a lecture, basically you're saying the video didn't work, I have to redo something, right? So this is just data-driven analysis of what we say is flipped learning, right? So clearly it's not because of any active learning mechanisms, it's really because of more passive, more on-time, more lecturing, and so on and so forth. And this is a finding that I find really intriguing and also predictable. That in some interventions where the classroom implementation also included active learning, the effect of flipped learning over classroom teaching vanished. So, in other words, if you want to improve even the direct instruction model, just do more active learning. Forget the modality. Yeah. And what this is a missed promise, really. You know, this is a perfect example of how we have a case of digitization without any transformation, because the underlying pedagogy remains the same, and the passive nature of learning remains the same. The average effect is likely coming from more time on task and more instruction. And that was causing the effect. So very depressing. But there was a beacon. In some of the flipped learning interventions, people had carried out problem-solving activities prior to instruction. And that was producing a significant effect. In other words, before people received any instruction or lecture, in some flipped learning interventions, they started by doing problem-solving activities. And that started to show an effect of learning, which, if you're familiar with my research, which is my main body of research on productive failure, which I talked about, that's very consistent with what productive failure is. And so the idea then came to us that how do we design flipped learning in a way that's consistent with the productive failure effect? So I'll just segue here very quickly to talk about what the logic of productive failure was. And this actually came forth from my early experiences as a teacher, the math teacher, as I was talking to you about. And the idea here was simple. If learning from failure is intuitive and compelling, we shouldn't wait for it to happen. We should intentionally, deliberately design for failure in a safe way and bootstrap that for learning. And so this is 20 years of research. A book is coming out on how this method works and how effective this is. So it's a two-phase design. We start with problem solving, carefully designed problem solving that leads to failure intentionally. And then after students have gone through that, you follow it up with instruction. So what we were finding in the flipped learning meta-analysis was quite consistent with this, that people, sometimes teachers intuitively have done a good thing, started with problem-solving activities, and then gone into instruction. So, and this productive failure effect, also other meta-analyses have also showed that this effect is also very strong compared to direct instruction, around 0.6 if you do it well, which is more than a year of schooling. So several studies, 166 about 2 years ago, have shown this effect, okay? So you have a flipped learning effect, which is very strong, of a year of schooling coming from more passive instruction. And then you've got the productive failure effect that is more active learning, problem solving followed by instruction that's even stronger, that's coming from a meta-analysis as well. And then there is a subset of flipped learning interventions that seem to follow the productive failure model roughly, that also show positive effects. So we weren't looking for it, but we came across it. So back to the flipped learning model then. So then we decided to say, okay, if you want to do flipped learning, what would work, given what we know from the data, from the meta-analysis, and the body of research on productive failure, which kind of came together serendipitously. So the idea was then to develop this model, and we called it the 4F model: fail, flip, form, and feed, right? And so the first phase, if you want to do a flipped learning intervention, is the fail phase. And here the focus is on problem solving in a safe space. So can we create safe spaces for students to generate multiple solutions to problems? These problems are new problems for which they may not have the knowledge to solve these problems, but still they're designed in a way that they can generate some ideas and solve them. Whether correctly or incorrectly, doesn't matter. But that's the space within which they discover what they know, the limits of what they know, and so on and so forth. So that's the starting point of learning. Then you go into the flip mode. Having done the fail phase, now is the time to give them some content. It could be through videos, could be through activities, could be through reading notes. And research shows that if you've tried something, and this is my own work and other research as well, that having tried something and not having achieved the correct outcomes, if you then read some explanatory notes or watch a video, it makes a lot more sense, and you learn a lot more if that happens. So the second phase is the flip phase, where you provide that instruction, you provide the expert knowledge, and you can do it in many interesting and engaging ways. And this time, it would work on the back of having failed. Next phase is the form phase, and this is where you could potentially reintegrate the lecture into the class, because lecture from an expert actually has value. You just have to time it well. The problem in the direct instruction model, as I see it, is that we don't time it well. So the form feed is absolutely important, where you need to deliver that expert lecture and deliver it in interesting and engaging ways, right? And finally is the feedback. So you do the problem solving and you provide multiple modalities of feedback, either through group work or instruction or tutorials or so on and so forth. And that creates the full pipeline of fail, flip, form, and feed, right? That's it. So the fail phase, flip phase, fix or form phase, and the feed phase. That's the 4F model. And we wanted to see if this works. Could we apply this in a meaningful way in a real ecology, in some context? So I want to share some evidence with you. This is the work of my PhD student, together with a math professor at ETH Zurich. And we targeted, as I always do, as a proof of concept, the most difficult math course a first-year undergraduate student can take. And it's not analysis, is linear algebra. Silence, right? So that means it is. So this is the large course, about this size. 700 students take it, and it's compulsory, and everybody has to take it. And it follows pretty much the direct instruction model. The lecturer goes into a big hall, delivers the lecture every week for a couple of hours, and then there are tutorial sessions after where students break into these tutorial groups and they do problem solving and application of what they've learned, right? And this is, again, a very good, Norbert is a really good lecturer, and he's lectured this for many, many years. What we did was to design the fail phase, and said, okay, we can't change much of the regular modality because it's a massive lecture, it's been going on for years. Let's design the fail phase. And so we inserted 30 to 45 minutes of problem-solving activities before key lectures, right? So we have a year-long lecture, the course, and we took 5 big ideas from semester 1 and 5 big ideas from semester 2. And for these 5 or 10 overall ideas, we designed problem-solving activities given prior to the lecture that would cover those concepts to solve those activities, right? So that's the key. These problem-solving activities are given prior to the lecture that covers those concepts. So we expect students will struggle. We expect students will not be able to solve them. And they're also designed in particular ways so that they can explore while struggling, right? So these are not standard problems. But they last about 30 to 45. And we ask them to do these online prior to the lectures. We explain to the student the logic model of this. We explain that research shows that this would be effective, that when they come to the lecture on the topic, they will understand the lecture better. So we had that, renegotiated that didactic contract because we want to create this safe space. But we did this. So 10 of these 30 to 45-minute sessions, in other words, our overall intervention time across the entire year was about 7 to 8 hours. That's it. Okay? 7 to 8 hours of surgically designed intervention time based on the 4F model and the productive failure model. Right? The historical passing rate, and in Switzerland we have the model where it's easy to get into the university, but it's hard to stay in. So the historical passing rate of this is 55%. Half of the class does not pass this. So here's a question to you. In your context, if you were to be able to design this, a year-long course which takes hundreds of hours of investment of time, and you will have a 7-hour intervention spread across the whole year, how much do you think we could move the needle on the 55%, if at all? This is not a rhetorical question. I want somebody to jump up and say, 1%. Go up to 80%. Aren't you optimistic? But I love the enthusiasm and the optimism. Any other takers? 5%, yeah. 5% would be a strong effect of a very good teacher, by the way. So you've got 5% and you've got 25%. Heterogeneity at work. Right. So what we found was, and we did this over, because it's design research, we did this over multiple iterations. In the first year, we could improve the needle by 10%. In the second year, we could improve it by another 10% as we brought it to high fidelity. COVID happened. It went down to 20%. It went down to 15%. The data is not there. My PhD student just graduated last year, and she showed that now that things have stabilized, the last implementation was back to 20%. Okay? So think about that. We didn't do any fancy modalities, any fancy tech, nothing. We just stuck to the basics. We looked at what the data was telling us. We looked at what research on productive failure was telling us. We designed a surgical intervention that lasted only 7 hours over the course of the whole year. And we moved the needle and kept it there, importantly, at 20% improvement. And that's what you can achieve if you stick to the basics. Right? So I return to the problem. I'm not sure how much time I have left, but I return to the problem. I shared with you at the start, the problem was Not that we learn poorly from bad lectures, but we learn poorly from very good ones. And I've shown you in the flipped learning literature how that is not happening, but given the data that we have from the meta-analysis, but also a way forward that if you were to redesign it in ways that are consistent with what we know from that research, as well as from related research on productive failure, that we can achieve very powerful effects on learning. Right? With that, I thank you. Oops.
Thank you. Now it's time for our second lecturer, Pattie Maes. She is Professor of Media Arts and Science at the MIT Media Lab. She runs the Fluid Interface Research Group, which does research at the intersection of human-computer interaction and artificial intelligence with focus on applications in health, well-being, and learning. Madam, the floor is yours.
Good morning. So Antonio started out this morning telling us that we live in a change of era. I would also like to argue that we are living at a moment of unprecedented rate of change right now. And the reason for that is generative AI, or AI finally being deployed in the real world. I would argue that this will, and already does, I'm sure, in a major way disrupt your whole field of education and learning. So I started, actually for me, AI is not new. I started on artificial intelligence research over 30 years ago in Brussels, Belgium. I got a PhD in AI. And I, soon after my PhD, moved to MIT because MIT was truly, at that time, the mecca for artificial intelligence research. But I soon became disillusioned by what my colleagues were trying to accomplish with their AI research. The goal of AI was really to model intelligence in systems, computational systems, and to match or surpass people. And I was always more interested in, can we actually augment human intelligence? Can we improve human intelligence, possibly with some of these same techniques? So right now, 30 plus years later, I feel like my colleagues in AI are still doing the same thing. They're basically trying to reach AGI, general artificial intelligence, and they're very busy making their models smarter, more accurate, etc. But they basically have dropped this big box of AI in the real world without any considerations for what this will do to human intelligence, to have this artificial intelligence at our fingertips. So that's what my research is focused on. I would argue that it is very important to look at what happens to human intelligence when we are assisted in real time by AI. And the reason is that AI for the foreseeable future is actually more likely to be used as an augmentation rather than an automation. So it's likely that people will be in the loop in some way or other, whether they are actively working with the AI or maybe supervising whether the AI is doing the right thing, etc. Economists and management scientists such as Eric Brynjolfsson of Stanford, previously MIT, or Darren Acemoglu from MIT, argue that augmentation will lead to better societal and economic outcomes. I also believe that augmentation with AI will be necessary for the foreseeable future because the current popular version of AI systems make a lot of mistakes. They hallucinate. So you need a human in the loop at some point to supervise the AI outcomes when it concerns really critical types of applications. I would also like to argue that for the foreseeable future, we need augmentation rather than automation, because many decisions and many processes that we are all taking every day in the real world require that people still have some understanding and control over the process, and that ultimately people are in charge rather than a system for many reasons, legal reasons and more. So if we look at the spectrum of work out there, I would argue that collaborative work between an AI and a human will consist the majority of the work, and there's only a little bit of work and processes that can be fully automated, and there will also, of course, always be a small category of tasks, etc., that will be 100% human labor. So AI is not just an engineering challenge. Because AI has to work with people, it is very much a human design challenge as well. We have to design AI for working with people so that ultimately people plus AI result in the desired outcomes. So can AI improve decision-making and critical thinking? I will show you that it is actually not, it doesn't necessarily follow that if you give a person one of today's AI systems, ChatGPT or whatever, that their critical thinking, their decision-making improves. In fact, it can decrease in quality, and that's what our and other people's research shows. When I started playing with ChatGPT and these other generative models, the first thing, of course, we thought about was, whoa, what if you had this system right with you all the time when you're reading things, you're listening to talks like this one, etc., and this AI system can fill you in on things, can tell you when the speaker is BSing, bullshitting, for those of you that don't know that one, and so on. So that was sort of our first idea, that this would be great. We would augment human intelligence by giving them this AI that is constantly with them and trying to help them decide on the accuracy of statements that you come across. So we built this system and we started testing it, a system that is with you when you read statements. And we had three conditions. A control group did not have an AI. A second group had an AI that just would say, this is true or this is false when you heard something. And a third group had an AI that could also, that would explain itself. So it would say, this is true because, or this is false because. And what we learned was that when people get an AI that just tells them this is true, this is false, when they hear or read statements, they don't significantly actually change their opinion. But when they get an AI, when they have an AI helping them, that also gives an explanation, they do in a significant way change their own prior opinion about the veracity or the validity of the statements. So we thought this is great. Explanations are important. When AI gives explanations, then people will use its recommendations more often. But then we started thinking sort of from a devil's advocate point of view, well, if explanations are so powerful, are they maybe a little bit too powerful? So we did an experiment where we had people assisted by a malicious AI, an AI that tries to, in real time again, convince you that the opposite is true of the real veracity. So for example, and of course, by the way, it's super easy to instruct, to give a prompt to ChatGPT to make it be a malicious AI. So we just told it, give an explanation for why this truthful statement would be wrong, etc., or while this wrong statement would be true, and it easily came up with interesting explanations. We then did an experiment where we had people first tell us, we had 1,000 newspaper headlines. People would first tell us whether they thought a newspaper headline was true or false. Then they would get the honest or the deceptive AI, and they would again say, and it would give explanations, both of them, and they would again then say whether that statement was true or false. This is the result in light blue, or all the way on the left in gray-blue. You see how good people are at discerning the accuracy of these newspaper headlines, true and false ones, without AI. In blue is witty AI that assists them in a good way, an honest AI. But in red, and on the left you have the total, the left graph is actually the total number of statements. On the left you see how much people's accuracy reduces when they have a malicious AI. So basically, malicious AI that gives you explanations works just as well as honest AI that gives you explanations. So we learned that actually what may be at stake here is that people are starting to overly rely on AI. They believe the AI too often, basically, especially when it gives explanations. And psychologists decades ago have shown similar things, that when you give an explanation for some bad behavior, people often accept it. Like if way back, Helen Langer, a psychologist at Harvard, did an experiment when people would still make photocopies. She would have a long line at the photocopy machine, and one person would come up and say to the front, "I'm so sorry, but I really have to make photocopies." And just because they gave a because, people would say, "Oh, sure, go ahead." So people don't necessarily process the explanation that is given. If there's an explanation, they often just glance over it and don't critically engage with it. So since then, we've been designing systems, interfaces for interacting with AI that are actually built differently. Right now, when you use AI, you give it a question, it gives you a page-long, usually, answer. And we've been changing that, and maybe it relates to Manu's work, actually, because we've been making the interaction such that the AI engages the user in more active thinking about the statement or the problem. For example, if one of our statements was, video games cause people to be aggressive because a gamer stabbed another person after being beaten in an online game of Counter-Strike. So if that is the statement, then you have to decide, is that overall statement true or false, that video games cause aggression? The system will not just say this is true because, or this is false because, but instead it says, it engages the user in thinking and says, well, if one person stabs someone after playing a video game, do you think that follows that then lots of people will do the same thing? So the AI forces the person to be thinking more deeply. And again, we did experiments with that and showed that that did increase the accuracy of the discernments. So for AI to be useful and successful in a human context, I would argue that it's not just sufficient for AI models to be accurate and fair and accountable and explainable and align with human values, but they should also be designed to work with people so that the combined system of people with the AI together results in the desired outcomes. So that's sort of the approach that we take in our work. Most AI research is on the left. They optimize AI for certain outcomes, then they drop it like that box in the real world and see what they don't even see what happens. Our approach is one where we try to design by designing it with and for and together with target users to optimize certain outcomes or objectives. Now, a lot of our work in my group goes beyond just helping people with AI for like looking at information and deciding on or processing information. I think that one thing that is holding back a lot of young people from reaching their potential is that there's actually some other skills that they are lacking that prevent them from being successful. So it's not always information, knowledge, skills, but it's also things like attention, motivation, grit, attitude change, behavior change, etc., effective communication. These are all incredibly important skills that don't often get taught in school, actually, and cause a lot of people to fail. So we have been looking at whether AI could actually help with those types of soft skills that could help people become the person they would like to be. One experiment that we did, and again, this relates to what Manu was talking about, was during COVID, everybody was learning online. We were inspired by one teacher in Japan who would always change his own representation on the video into a cartoon manga character that was very popular. You know how you could like be a cat and so on. And it turned out that his students loved it, even though whatever he was teaching had nothing to do with that. So we thought, well, what is the effect of sort of chain of personification of AI systems? And this is important because Meta, for example, has 3 billion users, and its AI has faces. You choose the face and the character you want to be your AI assistant. Tom Brady, who's a famous sports person in the US, and many other characters. So we did this experiment. We picked a person many people know, and back then, when we did the experiment in 2020, Elon Musk, who you may recognize, was more liked by more people. So we thought some people liked it, many people liked him back then. Many people already didn't like him, but he was sort of a good choice. And then we had a non-existing person, same age, gender, race, etc.
I am a virtual agent generated to help provide information. Today, I'd like to tell you about a type of vaccine known as live attenuated vaccines.
So what
the
we
info
did
in this presentation
is we had virtual Elon Musk. He introduces himself. He says, I'm virtual, and the other one as well. And we have them give a lecture on vaccines, the topic du jour back then. And we did a between-subject study with 134 participants where we looked at to what extent do you admire Elon Musk and how that correlated with learning outcomes. And we learned that the more people liked Elon Musk, the more they rated the instructor as a good instructor. And not just that, they also said, I want to learn more about vaccines. This was a really excellent lecture. I want to delve deeper into this topic, etc. Of course, if they hated Elon Musk, the opposite was true. But we thought that that was very interesting, that these characters can actually motivate people to learn, even though it's this element that has nothing to do with the topic necessarily. So we went a little bit further and we thought, well, what if for teaching history, I don't know about you guys, but it seems to me that history for most kids is always the least favorite topic in grade school. Of course, later you realize like how important history is. But we thought, well, what if we teach history with interactive characters? So we made this whole system where you can actually take a famous historical figure like Leonardo, but it can be anyone, and you can actually turn him into an interactive character to learn from him in his own words directly.
Hello, I am an AI-generated living memory of Leonardo da Vinci, an Italian Renaissance polymath.
So we have that virtual Leonardo who speaks to you, and you speak to Leonardo in voice. And we built a whole architecture so we can easily make virtual Marie Curie, etc. We start with the primary sources that that individual wrote. We then add secondary choices, biographies about the character, and we built a system that avoids hallucinations and inaccuracies by using what is called retrieval augmented generative AI. And so you can then come and talk to Leonardo about his machines, about where he lived, about who his mentors were, the people that he taught, etc. And we did a study again, 90 students in this case, and learned that we had some people read a book about Leonardo. And so you see curiosity, learning effectiveness, and motivation in the graphs. Then we had a group of people that interacted with virtual Leonardo for the same amount of time, just question and answer. And already we had some improvement. However, for significant, statistically significant improvement, we realized it was important that people first had to be introduced to Leonardo, because otherwise they didn't know what to talk about. So it was a little bit of a similar lesson where we learned you have to first introduce who this is, then you talk to him about whatever you want, and he pulls from his materials, and then that actually made significant difference in many of these learning outcomes. Another, apart from motivation, another problem for young and old people is attitude and behavior change. Very hard to help people with change in attitude, even if they may want to change. So let's first look at change of attitude. People always talk about AI being biased, and it's true. AI models typically are biased because they're trained on human data, and people are biased. But we thought, well, what if we, given that people are biased, people work with AI, what if we try to counter the bias of the user with an opposite bias in the AI? So we did exactly that experiment. We had an AI come up with problems for a set of with solutions for a set of problems, and depending on what their own personal values were, we actually gave them either a neutral agent that had neutral values, or one that was aligned, so pro, or one that was against, had the opposite type of values as they did. And we had people come up with a solution to a problem in those areas where we test their bias. Then we had them work together with an AI to come up with a suggested solution. And we learned that, yes, you can actually counter the bias of an individual with the AI. Of course, if you give them an AI that is aligned with their values, that is also biased in the same way, you get even more extreme solutions. So it's very interesting. We may want to look at values of a user and then create or design an AI that can best complement them in a direction that we want to accomplish. What about behavior change? Another really hard problem. So many people work on trying to help people with behavior change, and without much luck, including sort of novel technologies on wearables, etc. My student Pat depicted there in the leftmost picture, created this system inspired by the work of psychologist Hal Hershfield from UCLA, where young people, it's designed for people under 30, can upload their picture, and it first creates a prediction of what you may look like when you're 60, which you see at the bottom there. But then you also first tell the system about your goals. So you will say, for example, like the girl on the left said, I think I want to become a biology teacher, and I probably want to have 2 kids and live and teach in an inner city school, etc. And we sort of make a simulated future self, basically. So a guess as to what may happen in your life from now till when you're 60, based on what you tell the system your goals are. And again, ChatGPT helps us with that because it has tons of information about biology teachers, what they studied, what their path was, what they like and dislike about their job, etc. And so in just a few minutes, you have a future possible self. We tell people this is not a prediction of what will happen, it's just one possible future self. And you can talk to that future self over chat. So you just tell it like, tell me about a typical day in your life. What were some things that you really, some of the best moments in your career? What are some things you regret about being a biology teacher, etc.? So you talk to your future self, and that can help you with seeing that path from where you are to what you want to become, what you want to change to. And we did, again, a study, 344 people, together with Hal Hershfield, who focuses on this, and showed that people have less anxiety, or we had a control condition where people would just write about their future and what they imagine. And people who used our system, the interactive system, had less anxiety about the future. They were more motivated to study and do the things that they want, that would lead to that future, etc. They had a higher, what is called future self-continuity, which is the extent to which you think about longer-term goals in your day-to-day actions, etc. We also are now doing things like helping people learn about communication, for example, by rehearsing with simulated AI systems. All of us constantly have to have difficult conversations with family members, with colleagues, etc. And we decided that maybe people could benefit, just like you were benefiting from talking to your older self. What if you can talk to a simulation of the person you need to have a difficult conversation with, like you need to talk to your boss about getting a raise or something. With this system, you can basically create a synthetic agent that represents your boss, and you can have this whole conversation with your simulated boss asking for a raise, so that then you can potentially have more confidence, etc., once you go in there and have the real conversation. So we did this and also looked at third person versus first person. We learned that what is most effective, basically, is the third person point of view, where you act like a theater director who directs you to interact with this other character. And we had significant difference there in terms of people's confidence level, their empathy for the other character, and their sense of comfort for having that discussion in real life. So to conclude, AI is not just an engineering challenge. It is very much a people challenge, a human design problem, as well as a human design opportunity. So we should really aim to design for optimal performance of the combined human plus AI system, because the system will affect people as much as whatever decisions are being made. I would argue that if we don't design AI with human considerations, human users in mind, that this can, in the long run, result in de-skilling, for example. If you rely on AI to always help you with problem solving, of course, you may not become very good at solving those problems yourself. Disconnection from the material, but also from other people. Disinformation, you saw in the work I presented earlier, how gullible people are. And you don't just want an AI to give you all the answers. The AI should know when you should know the answer, or you should know how to derive the answer. And dehumanization as well. Thank you.
Okay, now you all, you know what you have to do. Make such a good presentation as we had here today, and be on time, okay? So it's time for the first coffee break. Welcome again. For questions, please, in the keynote, meet the keynote sessions, because they really deserve coffee break also. And thanks again for being here today. Welcome.